Hello everyone. Today I would like to introduce our recent work on domain generalization object detection by eliminating non-coarse vectors with a multi-view adversarial discriminator. We discovered that the coverage of non-coarse vectors in the limited source domains is incomplete. Traditional domain adversarial learning with single domain classifiers fails to comprehensively address all non-coarse vectors. To tackle this challenge, we propose MAD method, which consists of two novel modules, SCG and MVDC. The SCG module employs frequency domain augmentations to explore potential non-coarse vectors, while the MVDC module guides the feature extractor to ally features across different feature space. Through extensive experimentations across 7 different domains, we have successfully validated the effectiveness and superiority of our approach. For a long time, training object detection networks relies on the assumption that source and target domains are independent and identically distributed. However, in the real world, these models often face a drop in detection performance due to domain distribution shift. Domain adaptation methods were proposed to tackle this challenge. Such methods extract common features from labeled source images and unlabeled target images to adapt the model to the target domain. However, DA still require prior knowledge of the target distribution and retraining for different domains. Domain generalization object detection aims to obtain a model that can generalization to all target domains through a single training. We believe that the key of generalization is to guiding the feature extractor to learn causal features. We identify two problems with previous domain adversarial learning approach. Firstly, the common features in limited source domains are not truly causal vectors. For example, in the domains of sun and foggy weather, the significant difference is only represented by the blue shift indicating the weather, while the potential non-causal domain shift like lighting, viewpoint, and resolution represented by yellow are considered common features in limited source domains. This hinders the adaptation to potential target domain. Secondly, traditional DAL fails to handle broader domain variations. When we freeze the feature extractor parameters of a converged DAL network and introduce a residual module, we observed a continuous decrease in network loss. This indicates that achieving a balance in adversarial training does not guarantee the removal of all non-coarse vectors. Furthermore, visualization reveals that a single domain classifier can only focus on partial non-coarse vectors. Similar to human observed Penrose triangle can yield different interpretations. We believe that domain classifiers should pursue comprehensive coverage of non-coarse vectors rather than merely higher classification accuracy. To solve these problems, we propose a multi-view adversarial discriminator to comprehensively uncover and eliminate potential non-coarse vectors in the target domain. MAD consists of two novel modules, the spurious coloration generator and the multi-view domain classifier. The SCG module leverages domain random augmentation based on the frequency domain to introduce potential non-coarse vectors into training phrase. By applying a bandpass splitter, we divide the image spectrum into low-frequency and high-frequency components, where the former represents causal information and the latter represents non-causal information. We maintain the causal part unchanged and apply random transformation based on a Gaussian distribution to the non-coarse part. Finally, we merge this spectrum of these two parts and transform them back to the spatial image using the inverse discrete cosine transform. The SCG only requires a single source domain without additional reference images, and it can incorporate a rich set of potential non-causal vectors from the target domain. The MVDC module aims to break the balance of maximizing and minimizing the domain classifier loss in traditional DAL. We achieve this by replacing the original domain classifier with our multi-view domain classifier. The optimization problem is reformulated as the new formula, where each view consists of an autoencoder and a domain classifier. The structure of MVDC is illustrated in the diagram. During the training phase, we introduce three constraint laws. First, reconstruction laws ensure the consistency between the input to the encoder and the output from the decoder, thus preserving complete semantic information in the mapped future. Second, domain classifier laws ensure that different features from the same view have domain discriminability. Third, view different laws guarantee that each autoencoder maps features to different lantern space. Furthermore, at the image level, we employ the dilated convolutions to handle global non-causal features. At the instance level, fully connected layers are used to address semantic non-causal features among different instances. We also introduce a consistency loss between classifiers at different levels. Finally, the overall MAD loss is shown below. Next, I will provide a description of the experiments in this work. First, let me introduce some important experimental settings. We used 7 standard datasets in our experiment. Our method was implemented using PyTorch and -4 framework. As for the baseline, we select the two-stage fast RCN framework with the VGG16 backbone pre-trained on ImageNet. We first verified the effectiveness of the MAD method. Comparing the result with several baseline methods, it was observed that the MAD method achieved greater generalization performance in the majority of settings. Furthermore, we compared our MAD method with the mainstream DGOD task in the classical cityscape to foggy cityscape setup. Our method outperformed the existing DG method in object detection task. The performance of MAD surpassed some DA method even though they used target domain images during training. Additionally, we validate the generality of the MAD method by testing the model on 6 other datasets. Focusing on the common category car, MAD achieves the best performance in the majority of them. Moreover, the idea behind MAD was proved effectiveness on classification datasets. Furthermore, the TSNE visualization graph shows that our MAD approach could align them in all feature spaces. Finally, we performed some hyperparameter studies. It was observed that the network's performance increased with the number of viewpoints, but it reached convergence after exceeding 3 viewpoints. You can scan the QR code to access our paper and code.